So if you don't want to be recorded, your voice on the recording during the Zoom session, don't speak. Just send me a chat message and I will read that. So just because some people don't want to be recorded, that is my blurb for you. 100 centimeters equals 1 meter. And you have 10 meters times 5 meters times 2 meters, right? That's 10 times 10. That's 100 cubic meters. So to change that into centimeters cubed, 1 meter is 100 centimeters. So you have to get a cube. So you have to cube that, which means you have to cube this. So you actually have 1, 0, 0, 0, 0, 0, 0, 0, 0. 100 million centimeters cubed and 100 meters cubed. So that's the tricky part of that problem on that quiz.
That wasn't the problem I did.
You didn't do that?
No.
Well, that's the correct way to do that problem. Sorry. All right, so since you guys all pretty much watched the thing, we can just hop right into the lesson if there aren't any more questions. So in our book, we are in section 2.5, motion for constant acceleration problems. A lot of times we call these the kinematic equation problems. Right, and the kinematic equations have 6 variables: x naught, x, v naught, v, a, and t. This is initial position. This is final position. I'm just reviewing real quick here. This is initial velocity, final velocity, acceleration, and time interval. So those are the variables that we use to solve these problems. And they have 4 equations that we will use to solve every one of these problems. So the equations, I'll try to write these out. V equals V naught plus AT. X minus X naught equals 1/2 V naught plus VT. X minus X naught equals V naught T plus 1/2 AT squared. And V squared equals V naught squared plus 2A X minus X naught. So those are our 4 kinematic equations. So when we read through these problems, we want to pull out all 6 of those variables every time. So whenever we do these problems, we're going to start by writing those 6 variables down. And then we have to choose the correct equation that allows us to solve for the unknowns. So does everybody have a formula sheet from, or a piece of scrap paper you can write those formulas down on? There is a formula sheet in the portal that you can use for this entire unit. Oops, I just stopped my video. For the whole unit in the portal, over here under practice tests, there's a formula sheet for exam 1. And this is really handy. You can just print this out, and this will have all of the formulas that you need for the exam, and you can label them and write on here and use it when you're taking the test so you know exactly where the formulas are. And then when you're solving problems at home or when we're doing problems in class, you can have this out with you, and it'll allow you to find the equation much faster. So here is up here the formulas and the variables that we'll be using for these problems. Thursday, we'll go over the factor label method. And no, sorry, I got confused because another student showed up. Thursday, we'll go over kinematics in the Y direction, and we'll go from there. We do have another student that showed up. Who was the student that just showed up late? Was it? I didn't save it. Oh, son of a gun. Titus, show up. Titus? No Titus. All right, so we have 4, 7, 9, 13. Oh, we're still missing 1, 2 people. Who else was missing earlier? All right, so Thursday we'll do the kinematics in the Y, but today we are going to look in the X. And these problems, they seem a little scary, but if you're nice and neat about them, which I can't possibly be on this whiteboard, but I'll try my best, and take your time, they're really not that bad. The more you do, the better you'll get at them. So let's take a look at the first problem. We are on page 90. We're going to do number 20 on page 90. Now, when we're solving these problems, before I start number 20, there's steps to our process. And you probably saw these in the PowerPoint, but I'm going to go over them real quick. Number 1, read problem. Step 2, reread problem. Identifying knowns and unknowns. 3, choose equation. 4, solve algebra. 5, find solution. And 6, does answer make sense? So those pretty much are our 6 steps. I don't think I got them exactly the same as the PowerPoints, but we always read the problem just to give us an idea of what we're talking about. 2, we reread the problem and identify the knowns and unknowns. So we write down our variables. This is essentially writing down our variables right here. This is writing variables. 3, we go and we choose our equation that allows us to solve for our unknowns. 4, we do our algebra to isolate our unknowns. 5, we put our numbers in, find a solution. And 6, we say, does it make sense? If we're driving a car and the answer comes out to be 2,000 miles per hour, that really doesn't make much sense. So we would not use that as our answer. We would know we did something wrong. So those are our steps. So let's try number 20. And I'll go through and show you how I do these problems and how you probably should do these problems to make life easier for yourself. Number 20 says, an Olympic class sprinter starts a race with an acceleration of 4.5 meters per second squared. What is her speed 2.4 seconds later? And we're not going to do part B, the graphing. We're not doing PT graphs. So let's just write down our variables. We're going to reread this and fill in. So we have 6 possible variables: x naught, x, v naught, v, a, and t. So if we read through this, we say an Olympic class sprinter starts a race with an acceleration of 4.5 meters per second squared. Now she starts a race. We've all watched the sprinting race. We know the initial position is 0, and we know our initial velocity is 0. So we're starting from rest. It's implied here. It says she accelerates for 4.5 meters per second squared. And then in part A, what is her speed 2.40 seconds later? So that is a final velocity. What is her speed? And the time is 2.4. Fours just don't work well with this pen. 2.40 seconds. Our goal is, this is a question mark here. That's what this is. This is a question mark. Our goal is to find velocity. Our final velocity after 2.4 seconds. So what we do is now we have our variables. We reread. We found our knowns. We found our unknown v. That's what we're solving for. And now we need to go to our equation sheet and find the formula that allows us to solve for v. Notice, we do not have x. We do not have the final position. So when you go to choose a formula, you can't choose a formula with x in it. So right now, just at your seats, take a second, look over the 4 formulas. You don't have to make a right choice, but just in your brain, try to pick out which formula is the correct one to solve for v. I'll give you a minute here to think it, just to think. Did you find this formula? If so, you were correct. Notice we're looking for v. That's our unknown that we need to find. We need to find v. We have a, we have t, we have v naught. So our goal is to find this v. We don't have to do any algebra. We know this is 0 plus 4.5. I'm not going to write the units in just because of space. Times 2.0. V equals 10.80 meters per second. That's our final velocity. So we ask ourselves, does this make sense? Well, I'm not really very good at final speeds in the metric system, knowing how fast this is, but I do know that 25 meters per second is like 90 miles per hour, I think. So it's pretty good. You're going pretty fast after 2.5 seconds of racing. If you're a sprinter, we could convert it to miles per hour and see what it is. I mean, we can all use practice with the factor label. So we have 10.8 meters per second. We'll just change it into miles per hour. So 3,600 seconds, 1 hour, 1,609 meters are in 1 mile. Bet you didn't know that. So we can find here 22.37. No, that's not right. That's 24.16 miles per hour. So I was wrong about the 90. Yeah, 24.16 miles per hour. It's pretty fast. You're driving your car 25 miles per hour. I think somebody sprinting, a world-class sprinter could, an Olympic-class sprinter could keep up with your car. You've driven it at 25 miles per hour. So that kind of makes sense. Does anybody have any questions? And I totally didn't record that problem. Or did I? Did I remember to record? Let's hope. Remember I turned it off?
Yeah, big oof if you forgot.
Oh, I did remember. It says pause recording. Good, good. Whew. Does anybody have any questions on that problem?
Yeah. Is this coming straight from the textbook or no?
Yes, this is number 20, page 90.
Page 90, okay.
Sorry, I should have wrote that down. That's a good question. I think I mentioned it, but it's always good to write it. Page 90, that's a 90, not a 96.
It could be page 82.
Or page 82, depending on what book you have, right? The newer versions of page 90, this is the internet book.
Yeah, I got the internet one.
Yeah,
Is
the internet
different
one
than the hard
is,
copy?
well, if you go up to the top where it's got the little number page function, it should be 108. That's where it is for where page 90 is, because it's got all the extra stuff at the beginning, so you want to go to 108. That's
So in the hard book, it's page 108.
No, in the hard book it is page 90, but in the digital version with all like the stuff at the beginning, you can just skip to where it is to 108
Oh, on the
page-wise,
Adobe,
but in the actual thing, it's page 90 that it says at
gotcha.
the top of the page.
the Adobe file
Mine has
it as-
82.
like if you were going to print it out, it's 108 on the Adobe file.
Yeah.
My hard copy of the book is page 82.
Yeah, I think they came out with a new edition, but they're all the same problems, I'm pretty sure. They just
Yeah, yeah.
So that stinks on the homework then, doesn't it? Because there'll be different numbers on my Excel spreadsheet with the homework problems to do. No, it'll still be the same because it's still 1, 5, 7, and 8 you did, and they were the right answers. For chapter 1?
Yep.
All right, so hopefully they just changed the page numbers and added some fluff and didn't change the answers at the end. If you come across a problem that doesn't match up with the solution, let me know, please. I'd appreciate that. Just send me an email or whatever. All right, no questions on this particular problem? Let's try some more. We're gonna do this the whole time. And these problems can be really fun if you, once you start figuring out how to write the variables and stuff. So number 21, again, a well-thrown ball is caught in a well-padded mitt if the deceleration of the ball is 2.1 times 10 to the 4th meters per second squared, and 1.8 times 10 to the minus 3rd second elapses from the time the ball first touches the mitt until it stops. What's the initial velocity of the ball? So, all right, so again, we're gonna write down our variables. What I want you guys to do at home is to reread it and jot down in your notes what you think the variables are. What you think the correct number, the number value that corresponds with the variable. All right, so let's see what we got. We got a well-thrown ball is caught in a well-padded mitt if the deceleration of the ball is 2.1 times 10 to the 4th meters per second squared. Well, deceleration, the ball is slowing down. So this is negative 2.10 times 10 to the 4th. Oh, these fours. 10 to the 4th meters per second squared. It's got to be negative. It's slowing down. And 1.5, we have the time. 1.5 times 10 to the minus 3rd seconds. 1.85 times 10 to the minus 3rd seconds. Elapses from the time the ball touches the mitt until it stops. So which variable is stops? Well, that is X. Oh my goodness. That is V. V is the final velocity is 0. The initial position is 0 in the mitt and it goes a certain distance, which we don't have. Our goal is to find the initial velocity. All right, same equation as last time. It makes it easy. Now we have to get V naught by itself. So we got to get V naught over here. So we subtract it from both sides. We know this is 0. That makes life easy. So this gives me negative V naught equals AT. V naught equals negative AT. V naught equals negative 2.1 times 10 to the 4th. Look at that 4. Times 1.85 times 10 to the negative 3rd. And our initial velocity, when I put this into my calculator, (38.85 meters per second). So in the last problem, we had what, 10.8, 11 meters per second, and our velocity was 23 miles per hour. In this problem, we have 38, which is roughly 4 times more, less than 4. So the velocity in miles per hour is going to be less than 100 miles per hour, so roughly 85 miles per hour. So that sounds like a pitch into a catcher's mitt. I'm going to go with 38.85. This is approximately, I think, like 85 miles per hour. That's my approximation just based on our results from the last problem. So I think that's pretty good. Step 6, it goes with what we got. Anybody have anything need clarified there? All right, we are going to go to the next problem we have to do tonight. Number 25 on the next page. And I'm just going to go ahead and write my variables down. I know they're coming. I switched up the order on you, but it doesn't matter. And then we're going to read it. At the end of the race, a runner decelerates from a velocity of 9 meters per second at a rate of 2 meters per second squared. How far does she travel in the next 5 seconds? What is her final velocity? Does this result make sense? All right, so again, reread it on your own and try to pull out the variables. All right, let's go through this problem. At the end of the race, a runner decelerates from a velocity of 9 meters per second. There's our first piece of data. That's our initial velocity. At a rate of 2 meters per second squared. How far does she travel in the next 5 seconds? So the time here is 5 seconds. Our initial distance is 0, and we're looking for a final distance. That's in part A. We'll put an A here for part A. And in part B, it says what is her final velocity? Part B. So we got 2 parts. I have a limited amount of white space, so I'm gonna have to be neat. First part, we gotta find X. X is our final position. And we don't know V. Look over your formulas and figure out which formula we can solve for X without knowing our final velocity. Did you get this one? I hope so. We want to solve for X. So we come up here. We know X naught is 0, so X minus 0, we can just take that out, equals 9 times 5 plus 1/2 times -2 times 5 squared. Put that into our calculator. And we get 20 meters. I could have done that without my calculator, but I want to make sure I'm right here. That's how far we've gone. 20 meters. Does anybody need anything clarified there? That's part A. Part B, we want to find our velocity. So we can use our favorite one from the last. So -9 plus -2 times 5. Our final velocity is -1 meter per second. And the question in part C says, does that answer make sense? So, all right, we're going to do a little poll. Thumbs up if it makes sense, thumbs down if it doesn't make sense. Thumbs up, it makes sense. Thumbs down, was it thumbs up, it doesn't make sense? I got myself confused. Thumbs up, it makes sense. Thumbs down, it doesn't make sense.
There's no thumbs down.
There's no thumbs down?
No.
There's
Scary
only
face.
just like a few reactions. There's like clap, thumbs up, heart, crying, laughing emoji, surprise face, and ta-da.
Surprise
I
face.
just do
If
like
it's-
happy face.
surprise face if it is not looking good. Like that. That's the surprise face.
I mean, it makes sense. I just have been doing my math wrong because I didn't get the final velocity or x, so that's cool.
Are you using the negative sign?
I'm not sure, but I don't think I got the right numbers. Give me 1 second to finish it.
This is 9 minus 10, right? Negative 2 times 5 is negative 10, so it's 9 minus 10. And this is 45. These two cancel, give you negative 1, and that's 25. So 45 minus 25 is 20.
Oh, I wrote down the time as not a -2. My bad.
That's the acceleration is negative 2. Time can't be a negative because then you'd be going backwards in time. So why does V not make sense? That's the question, or you guys mostly know, because think about it. If we're slowing down, right, we're going 9 on our Cartesian coordinate axis, and we're slowing down. So we're over here, we're going 9, we're slowing down. That means we're coming backwards. We're changing directions. I'm doing velocity, but I meant to do position. If you look at our position versus time. So here's our position and this is our time. If we're going in the opposite direction, that's what this -1 tells us. So essentially, we're going to be changing from a positive and we're going backwards, which can't happen. And these graphs probably aren't helping because essentially you're walking forward, you're stopping, and you're turning around. That's what our acceleration is telling us. So it cannot happen. It's bad. Bad answer. The problem is the time is too long. So you run a race, you get to the finish line, and you keep slowing down is what it's telling you for longer than you needed to. It's kind of weird. But this is just showing you how the one that doesn't make sense. Does anybody need anything clarified there? All right, you guys, I want you guys to try an entire problem at your seats here. Number 27, the slap shot, hockey. It's a little I'm a little sensitive about hockey right now, so hopefully your good answers will cheer me up. Try number 27 at your seats on your own. If this shot takes 3.33 times 10 to the minus seconds, calculate the distance over which the puck accelerates. Let's reread it. And the slap shot accelerates from a velocity of 8 to 40. So the initial velocity is 8 meters per second. Final velocity is 40 meters per second. If the shot takes 3.33 times 10 to the second seconds, so the 3.33 times 10 to the minus second seconds, calculate the distance over which it accelerates. So we assume the initial position is 0, and we're trying to find x, and we don't know a. So the formula that we choose, x minus x naught equals 1/2 v naught plus v times t. X equals 1/2 8 plus 40 times 3.33 times 10 to the minus second. X equals 0.79 meters per second squared. I mean, this is not meter, this is distance. X equals 0.79 meters. So that's pretty much how long the puck is on the stick, for almost a meter. That's what they're asking you here. Does anybody have any questions on that one? Don't be yawning during class. I can't see who it is, but I heard it. It's probably the one person that's not muted. All right, let's try one more. You guys have to do your homework before Thursday because we're going to do more of this on Thursday, just in the Y direction. So you want to have as much practice as you can. Plus you got the quiz. So you should have 20 problems under your belt, including the ones we did here tonight together. Let's do 36. Where's my pen? And just parts A and B. Just A and B. C and D are just kind of weird. We just want to do 36 A and B. And we'll do it the same way we did it before, where you can chat me questions. You can chat me questions about the last problem if you want, or you can just solve it and put your thumbs up when you're done. An express train passes through a station. It enters with an initial velocity of 22 meters per second and decelerates at a rate of 1.150 meters per second squared as it goes through. The station is 210 meters long. How long is the nose of the train in the station? How fast is it going when the nose leaves the station? So when it says the nose, right, that's the front of the train. So it's entering and then it's leaving. So this distance here, that's the 210 meters we're talking about from the time the nose hits from one point to the next. So our initial position is 0. Our final position is 210 meters. Our initial velocity when it hits the station is 22 meters per second squared. Or meters per second, excuse me. We're looking for the final velocity, and the whole time it's decelerating at negative 0.150 meters per second squared. Our goal is to find the velocity. So we got to choose the equation. V squared equals V naught squared plus 2a x minus x naught. We don't know t, so we have to choose the equation without t in it. Now we just plug our variables in. V squared equals 22 squared plus 2 times negative 0, negative 0, make it big, 0.15 meters per second squared times 210. So V equals, this one I can't do in my head. .52 meters per second when it leaves the station. That's our final velocity of that train. You can see it makes sense. It wasn't slowing down that much, 0.5 meters per second squared. So it went from 22 to 20.52. Not a ton of velocity loss there. All right, so what I'm going to do is I'm going to stop this recording. Those of you who are good can leave. Those of you who didn't have a clue what you were doing on any of those problems, I would suggest you stick around and ask me some questions. If I can figure out how to stop the recording. So part B is easier to actually do part B before you do part A, because now you have everything, so you can just solve the time. V equals V naught plus AT. T equals V minus V naught over A. T equals 20.52 minus 22 over negative 0.15. So our time is negative 9.87 meters. Oh, sorry, negative 9.87 seconds. for part A?
It must be written differently in my book then.
What's that?
Part A is how long is the nose of the train in the station?
Yeah, that's time. Not
Oh.
210 is distance.
Oh, I see it now.
You got it?
Yes. Thanks.